Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Core Shell Semiconductor Nanocrystals from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, core shell semiconductor nanocrystals are discussed and the electronic structure is studied. Also, the classification of core shell nanocrystals is presented in this module. In addition, synthesis and characterization of core shell nanoparticles is studied. Finally, the various applications of core shell nanoparticles in the field of biomedicine and optics are highlighted over here. Now, what are core shell semiconducting nanocrystals? Core shell semiconducting nanocrystals are the materials whose properties are intermediary to those of individual atoms or molecules and the bulk, that is semiconductor crystals. They have novel properties and the properties are dependent upon their size. A core shell nanocrystal comprises a semiconducting quantum dot core and a shell of different semiconductor. Core and shell usually comprise type 24, type 44 and 35 semiconductors. Typically, core shell examples include the heterostructures such as cadmium sulfide, zinc sulfide, cadmium selenide, zinc sulfide, etc. Organically passivated quantum dots exhibit low quantum fluorescence yield because of surface related trap states. The shell protects the nanocrystal against environmental variations, and also it is a protection against degradation caused by photooxidation, and I can say it is another means to control the properties of crystal. The emission wavelength can be varied over a broad range by precisely controlling the size, shape, and composition of both the core and the shell. This is more effective way to control emission properties than individually controlling the core or the shell. The material has extensive applications in biological systems as well as optics. Coming on to the background of core shell semiconductor nanocrystals, colloidal semiconductor nanocrystals or quantum dots are approximately 1 to 10 nanometer in diameter, and they have organic ligands which are attached to their surfaces. Owing to the size-dependent electrical and optical properties, these nanocrystals have extensive applications in nanoscale photonics, photovoltaics, LEDs, etc. Quantum dots are replacing organic dyes as fluorescent markers in biological imaging as well as biosensing because of their tiny size, adjustable emissions, and photostability. Figure 1 shows the TEM image of NaYF4, YB TM nanoparticles coated with zinc oxide, which is shown in the top left figure, The associated chemical maps clearly confirm their chemical composition. Luminescence in quantum dots results from exciton decay, that is, electron hole recombination, which might be radiative or non radiative. In radiative decay, electrons relax from conduction band to valence band via emitting photons. The wavelength of the emitted photons is equal to the band gap of semiconductor. In non-radiative recombination, the electrons relax by releasing their energy by emitting phonon or Auger recombination. At nanoscale, quantum effects result in size-dependent increase in the band gap and quantization of energy levels. This quantization of energy levels in quantum dots renders the electronic structure intermediary to individual atoms or molecules which are having single homo-LUMO gap and also bulk semiconductors which are having continuous energy bands. Figure 2 shows the electronic structure of bulk, quantum dot and single molecule. The crystal structure of semiconductor nanocrystals is usually identical to the bulk counterparts. However, the lattice periodicity abruptly stops at the surface of nanocrystals. Thus, surface atoms have lower coordination numbers than the atoms which are present in the interior of nanocrystal. Due to this incomplete bonding, in comparison to the interior atoms, atomic orbitals point away from the surface. This results in dangling orbitals, which is also known as unpassivated orbitals. The dangling orbitals present at the surface of nanocrystal are localized and are slightly charged, that is, they are positive or negative. A hypothetical band structure is assumed to be formed owing to the weak interactions among inhomogeneously charged energy states which are present at the surface. Electrons and holes can be trapped at the surface when the energy of dangling orbital is within the band gap of semiconductor. For example, in cadmium selenide quantum dots, cadmium dangling orbitals trap electrons, whereas selenium dangling orbitals trap holes. Moreover, charge carriers can also be trapped by any surface defects in the nanocrystal. Due to the trapping of charge carriers of the surface of quantum dots, the probability of non-radiative decay increases. This results in a corresponding decrease in fluorescence quantum yield. To passivate these surface traps, organic ligands are used to coordinate with the surface atoms. For example, triacetyl phosphine, that is TOP, and tri-N-octyl phosphine oxide, that is TOPO, are generally used to passivate the surface traps and for growth condition control in high quality cadmium selenide quantum dots. Even though this technique produces high quality quantum dots with uniform size and good crystallinity, the quantum yield is approximately 5 to 15%. Let us next study the classification of core shell nanocrystals. The properties of core shell nanocrystals arise from relative alignment of conduction and valence band edges of core and shell materials. In the case of type 1 semiconductor heterostructures, both the charge carriers, that is, electron and hole, remain localized within the core, while for type 2, one carrier is localized in the shell and the other in core. Figure 3 shows the three types of core shell nanocrystals. The upper and lower edges are the upper and lower energy edges of core and shell particles. The core shell structures can be classified in the following types. First is the type 1 core shell nanoparticles. In type 1, core has smaller band gap than the shell, and the conduction and valence band edges of core lies within the band gap of shell. This results in confinement of both electrons and holes within the core. This is shown in figure 4, where an exciton at cadmium selenide or cadmium sulfide interface occupies energy states in the cadmium selenide core corresponding to the lowest energy separation. Radiative recombination within the core emits the light of wavelength which is redshifted relative to the uncoated cadmium selenide. Typical examples include cadmium selenide, cadmium sulfide, cadmium selenide, zinc sulfide heterostructure, indium arsenide, cadmium selenide heterostructures, etc. Figure 4 shows the energy level diagram of type 1 core shell heterostructure, where a heterostructure is formed by the cadmium selenide core and the cadmium sulfide shell. Another type of core shell structure is the reverse type 1. In this case, the band gap of core is larger than that of shell, and the edges of conduction and valence bands of shell lie within the band gap of core. Lowest available exciton energy separation occurs when charge carriers are localized in the shell. The wavelength of emitted light can be tuned by varying the thickness of shell. Typical examples include heterostructures such as cadmium sulfide, mercury sulfide, zinc selenide with cadmium selenide, etc. Coming on to type 2 core shell structures. In this structure, both conduction and valence band edges of core are either higher or lower than those of the shell. Figure 5 shows a typical example of this case where the band edges of the core, which is the zinc telluride, having a band gap of 2.26 electron volt, are higher than the shell, which is of cadmium selenide, having a band gap of 1.74 electron volt. Lowest energy separation of exciton occurs when hole is confined in the valence band of core, that is zinc telluride, and electron is confined in conduction band of shell, that is cadmium selenide. The wavelength of emitted light is determined by the energy difference between these occupied states, which is indicated by the red arrow in figure 5. Thus, the wavelength of emitted light is lower than either of the individual band gaps. This results in considerable redshift in the emission wavelength in comparison to the unpassivated core. Typical examples include the heterostructures such as zinc telluride and cadmium selenide, then cadmium sulfide and zinc selenide, etc. Another type of core shell nanocrystals are of the doped core shell semiconductor nanocrystals. Doping can be used to effectively alter the optical properties of quantum dots. The impurity content in quantum dots produced via colloidal synthesis is lower than their bulk counterparts. The most popular applications of quantum dots which involve doping include magnetic memory and spin-based electronics. Doping has been found to strongly influence the magnetic properties of core shell nanocrystals. For example, doping the shell with manganese in cadmium selenide zinc sulfide heterostructure made the nanocrystal paramagnetic. Let us now come on to the synthesis of core shell nanostructures. Core shell nanostructures have been prepared via various wet chemical methods, including chemical precipitation, sol gel, microemulsion, and inverse micelle formation. Chalcogenide core shell nanoparticles have been prepared from these techniques with emphasizing better control over size, shape, and size distribution. To control the optical properties of these nanoparticles, various support matrices have been used. For example, glass, zeolite, polymer, fatty acids, etc. Additionally, nanoparticles of sulfide, selenide, and telluride have been prepared via Langmuir-Blodgett film method. Electrochemical technique is always preferred over wet chemical methods due to the possibility of using aqueous solvents instead of toxic organic solvents. Also, there is a formation of conformal deposits. Then the deposition takes place at room temperature. It is inexpensive. In addition, there is a precise control over composition and thickness of the semiconductor coating on metal nanoparticles. Nonetheless, electrochemical synthesis of core shell structures is rather difficult because of the challenges which are involved in producing electrically addressable arrays of nanoparticles. There have been recent reports about the electrochemical synthesis of core shell cadmium selenide and cop- cadmium sulfide and copper iodide nanoparticles on a three-dimensional nanoelectrodes via layer by layer deposition of alternate layers of nanoparticles and polyoxometallic, that is POM. Colloidal synthesis of core shell semiconductor nanocrystals can be performed with proper control of the reaction kinetics. This method provides great control over size and shape of the semiconductor nanoparticles, and various types of nanostructures have been grown with this technique, such as dots, tubes, wires, etc. These methods demonstrate exciting these materials demonstrate exciting electrical and optical size dependent properties. Owing to the synergistic effects of close contact between core and the shell, core shell nanoparticles offer novel properties. Also, they exhibit improved functions which are not observed in individual particles. it is possible to control the size of core and the thickness of shell during synthesis process. For example, volume of H2S gas influences the size of cadmium selenide core nanoparticles during synthesis in such a way that the size of core decreases with an increase in volume of H2S. Also, the size can be reduced by rapid cooling of the products. The thickness of shell depends upon the quantity of shell material which is added during coating process. Let us next move on to the characterization of semiconductor nanocrystals. The wavelength of the emitted light increases with an increase in either the size of the core or the thickness of shell. To passivate the relaxation pathways and increase the radiative states, the interface between core and shell can be modified. Since the nanoparticles exhibit size-dependent band gap, which is arising from quantum confinement, the photoluminescence color from the nanoparticles can be tuned from blue to red by altering the size of nanoparticles. Thus, the luminescence color as well as purity can be tuned by adjusting the size and shape of nanoparticles. Nonetheless, the surface traps limit the quantum yield and luminescence brightness of the core shell nanoparticles. Core shell semiconductor nanocrystals can be characterized by UV visible absorption spectra, X-ray diffraction, transmission electron microscope, and X-ray photoelectron spectroscopy. We will next study the applications of semiconductor nanocrystals. The key property of core shell nanostructures is that the quantum dot cores exhibit strong fluorescence, which is essential property in their optical and biomedical applications. Further, the shells can also be manipulated to control the bulk properties, for example, solubility, reactivity, etc. Coming on to the biomedical applications, the desirable properties of core shell nanocrystals for their biomedical applications are high quantum yield, narrow fluorescence emission, broad absorption spectrum, photostability, moderate fluorescent lifetime, approximately 20 seconds, and high brightness. High quantum yield implies minimum energy required to induce fluorescence in the quantum dots. Narrow fluorescence emission is important to emit multiple colors simultaneously with no color overlap between different types of core shell quantum dots. Broad absorption spectrum allows multiple quantum dots to be simultaneously excited at the same wavelength. This allows simultaneous imaging of multiple quantum dots. Time-resolved imaging requires around 20 seconds fluorescent lifetime. Additionally, the core shell quantum dots are compatible with organic fluorophores. These quantum dots are stable against photobleaching. However, the performance vis-a-vis fluorophores needs further investigations. Besides, 2-photon fluorescence efficiency of core shell quantum dots is around 100 to 1000 times than that of organic dyes. For biological applications, the quantum dot core can be covered biocompatible shell such as DNA, for specific targeting. In addition to this, an organic molecule can also be used as the shell with which another biomolecule can be conjugated at a later stage. Typical examples of core shell materials used are cadmium selenide zinc sulfide heterostructures, cadmium selenide, cadmium sulfide heterostructures, etc. The addition of shell protects the core from photobleaching as compared to using core material alone. Fluorescence color can be tuned by controlling the particle size. Nonetheless, further study on the effects of shell molecules, pH, temperature, etc. in the properties of core shell nanoparticles is required. Let us next study the in vitro labeling. Owing to the possibility of imaging multiple colors, core shell quantum dots are important for cell labeling. An important challenge to use core shell nanoparticles in cell labeling is the difficulties involved in passing them through the cell membrane. Various techniques have been adopted to achieve this, such as endocytosis, direct microinjection, and electroporation. After entering the cell, these nanoparticles aggregate in the nuclei and remain there for prolonged time spans. Since core shell nanoparticles stay in the cells even after cell division, both mother and daughter cells can be easily imaged using them. This has been demonstrated in the case of xenopus embryos. Core shell nanocrystals can also be used for tacking. This is achieved by growing cells on a two-dimensional matrix which is pre-embedded with core shell nanocrystals. As cells move, they uptake these nanoparticles, thereby leaving a trail which can be seen in the form of the absence of nanocrystals. This is clearly shown in the figure where a media with orange core shell semiconductor nanocrystals is considered. The cell uptaking core shell semiconductor nanocrystals from media is shown along with the path left by the cell. In this way, the mobility of the cells can be observed, which is important since the metastatic potential of breast tissue cells has been shown to increase with mobility. Furthermore, 5 different core shell nanoparticles have been shown to simultaneously detect 5 different toxins. Environmentally friendly and less toxic core shell structures have been prepared by using silicon quantum dots which are coated with different shells. Silicon is 10 times safer than cadmium, and present work is focused to make silicon more hydrophilic and biocompatible. Particularly, silicon quantum dots with polyacrylic acid and allylamine shells have been used in cell labeling. Other in vitro uses are flow cyclometry, pathogen detection, and genomic and proteomic detection. We will next study the in vivo and deep tissue imaging. Core shell quantum dots exhibit emission in NIR, that is 700 to 900 nanometer region of the electromagnetic spectrum. Thus, the imaging is not affected by the autofluorescence from the tissues, which is 400 to 600 nanometer, and scattering effects. This has been used to map sentinel lymph nodes in cancer surgery in animals. In a study, 1 centimeter deep lymph nodes were imaged, and the excised nodes with nanoparticles accumulation were found to have the highest probability for containing metastatic cells. core shell quantum dots have been demonstrated to remain fluorescent within the cells in vivo for up to 4 months. To track and diagnose cancer cells, labeled squamous carcinoma cell line U14 cells were used and fluorescent images were observed after 6 hours. Core shell quantum dots conjugated to doxorubicin have been also used to target, image, as well as detect prostate cancer cells which express the prostate specific membrane antigen proteins. Conjugating nanoparticles having polymer shells to cancer specific antibody is the most frequently used tumor targeted imaging. An important concern for use of core shell nanoparticles is to image in vivo is regarding their excretion and toxicity. There have been reports showing DNA damage and toxicity towards liver cells. Besides, the use of shells have shown to reduce these ill effects. Presently, cores which are made from rare earth elements as well as silicon are being studied for reducing toxicity. Other concerns are limited commercial availability, variations in surface chemistries, non-specific binding, and instrument limitations. Then coming on to optics, the optical properties of the core shell quantum dots are decided by the band gap, which can be tuned by modifying their size, shape, and composition. Thus, by tuning these attributes of the core shell quantum dots, they can be optimized for use in optical devices like LEDs, photodetectors, lasers, photodiodes, photovoltaics, etc. So students, let us summarize what we have learned in this module. In this module, core shell semiconductor nanocrystals were discussed and the electronic structure was studied. Also, the classification of core shell nanocrystals was presented in this module. In addition, the synthesis and characterization of core shell nanoparticles was studied. Finally, the various applications of core shell nanoparticles in the field of biomedicine and optics were highlighted. Thank you, students, for your attention.